Hello everybody, and today we will talk about the reduced echelon matrices, which is the first part of the first video lecture for the chapter 1.2. Okay, so let's just start. So what are the echelon matrices? It's basically matrices with a lot of zeros, but very, very well organized zeros. For example, all non-zero rows of the echelon matrix are always about full zero rows. So for example, here we have matrices without zero rows, but the second one on the right have a bunch of zero rows on the bottom, but non-zero rows are above it. Then there is always a leading entry, which is basically any non-zero number. So if you take every row, so that would be well organized, first bunch of zeros and then one non-zero element. And after that, these little stars denote any other number. It can be zero, non-zero, complex, real, doesn't really matter. Okay, another important property of the echelon matrix, if you try to go down kind of diagonally through the matrix, the leading entries will move to the right. And probably this is very confusing with all these leading entries, stars and boxes. So let's just look on actual real matrix. So here, for example, there is a matrix. Let's try to figure out if it's actually echelon matrix or not by looking at our three property. First, we start with the first property, non-zero rows should be above zero rows. Okay, no zero rows here, so we can move to the property number 2. Leading entries has zeros below. Okay, so we need to find leading entries. In the first row, okay, this is pretty nice. We have the most left element 1. And the zeros below, okay, it seems to be working here. So moving to the left one, there is no leading entry here. So let's move into the next one. So here is the leading entry 2, and there is a zero below. And the final leading element is 1 over here, and there is no rows below. So the second seems to be holding through. Okay, so now let's look at the third property. We're going down through the matrix and leading entries are always moving to the right. Okay, it's more, look like they do move to the right. So this matrix indeed an echelon matrix. Okay, so and let's look at another type of echelon matrix. It's even more reduced and it's called reduced echelon matrix. So now our leading entries are actually not any number, but precisely 1. And another interesting property of reduced echelon matrix that our leading value 1 is the only non-zero value of a column. So you can look at every column and there is only one non-zero value, and this is the leading entry. Very neat looking matrix. So let's look at another example here. So let's look at these matrices with the numbers, and we'll try to figure out if this is actually in reduced echelon form. Okay, so let's look at the first three property, non-zero rows above zeros, excellent. Then leading entry is equal 1, so there is our first column with leading value 1. The second column also leading value 1. The third row column does not have leading value, so we can skip it. And the fourth row is also doesn't have a leading values. Okay, excellent, seems to be working. Now, leading entry is the only non-zero entry in its column. Okay, let's go to the columns one by one. Yeah, the first one seems to be holding true, only 1 0 and the rest of only 1 1 and the rest of zeros. The second column, again, only 1 value is not 0, and it's a leading element. The third column seems to have a problem. We have here, in addition to leading values, this -5, which is clearly not 0. So this matrix, although very neat, is not in the reduced echelon form. And this is how you usually check if your matrix. Just follow this definition, these 5 rules. So, and why do we fussing so much about the echelon matrix? It's because they are unique, a special reduced echelon matrix. For every even given matrix, any matrix in the world can have only one reduced echelon form. And that's unique, and that's why it's referred to uniqueness property. Okay, so now let's just bring a couple more definition to kind of make us easier to work with our matrices. For example, in reduced echelon form, we call a pivot position is a location of our leading value. For example, here for the first column, there is the pivot position here on the top equal 1. On the second row, again, we have a pivot position is in the second row, and so on so far. So we have here 2 pivot positions. Also, we refer the column which contains a pivot position, a pivot column. Okay, so and just look at, let's look at the example of the real matrix with the real numbers. So again, we have a pivoting position here in the first row, and there is a pivoting position in the second row. Okay, so now when we have all these definitions, let's try to use them to reduce a matrix here, very nice, neat matrix, to a reduced echelon form. And again, I try to find as easy matrix as possible, and I also use a color coding here to make working with the rows easier. Okay. So we have this matrix in reduced echelon form. We will just have 2 pivot columns, first and the second, and both of these columns will have only one non-zero element. Okay, how we make this matrix out of that? We can start from the first column and follow through. For example, here, if we look at our first column, then we should make our pivot element here on the first position of the first row. And that would be our pivot column. There is only one problem here. Below pivot element, leading element should be a 0, and we have 4. So we need somehow get a 0 here. We can use our row operations. We subtract 4 times row 1 from the second column and get our desired 0 in the second row. Okay, so now we can move to the next pivot column. And this -3 should our pivot element, but if it's our pivot element, it should be 1, not -3. So somehow we need to get the 1 here. And again, we can just divide second row by -3. And again, we will get desired 1 in the pivoting position. Okay, so now we have 2 pivot columns with only one small problem. So here above 1, we should have a pivot, a non-pivot element, and it should be equal 0. So again, we can use the row operation. We can subtract double of the second column from the first one. And finally, we will get our reduced echelon matrix. So it's look exactly the same as we desired. So, but now instead of the stars, we have -1 and 2, which help us to actually find solution to our system. And this is the most beautiful things about reduced echelon matrix, because there is only one non-zero element in the column. It's basically automatically give us solution to our system, but only if this solution exists. And we would talk about the existence and uniqueness of solution of reduced echelon matrix in our next mini lecture.